Internal energy is something that is a state function. So, a state function is a function where the value depends only on the state of the system, not how you got there. So, it's a variable that depends on where you are at the moment that you're looking at it. It doesn't matter how you got there. So, change in energy is an example of this, right? If we just want change in energy, we do final minus initial. The path that it takes to get from the initial to the final doesn't matter. So, a path function is one where it depends on how you get there. Now, I don't know, with gas prices, what they are recorded for posterity at this moment, I can't imagine they'll be any lower when this is listened to in the future. Um, this example may start to not be as good, but let's look at this example. Let's say that you want to travel from St. Louis to Chicago. So, my question to you is, how are you going to do this? And right here's my terrible drawing of the state of Illinois, or part of it, and the part of Missouri. It's pretty bad. Either way, you can kind of tell that it's Illinois and Missouri. Um, I have different ways to get to Chicago. So one, you could drive. Let's say you drive and you take Interstate 55 the entire way, right? That's this orange line. It pretty much goes from St. Louis to Chicago. You can kind of just do this diagonal line across Illinois. So that's one way to get from St. Louis to Chicago. The other way, if you're driving, that is the closest to being direct. You take 70 and then from 70 get on 57. Take that north till you get to Chicago. Option three, you could fly direct. So it's my green line, a little puddle jump from St. Louis to Chicago. Four, let's say you fly and looks like I've got a layover in Minneapolis at this point, but a layover anywhere. So you fly out to some other city and then fly into Chicago. There are other ways that you could get there, but looking at these four, some of the data about this trip would fall under being a state function. So the things that don't matter how you get there, things like your change in altitude. What's the altitude difference between, well, I guess Chicago's your final state, so altitude in Chicago minus altitude in St. Louis. Change in latitude, change in longitude, right? Or even just like your altitude in Chicago doesn't change because it does not matter how you got to Chicago. The altitude that you are at is the thing being measured. The path functions, so things that depend on how you get there, total miles traveled, total money spent, total time traveling, those are things that would add up depending on the path that you take to get there. So here's just a non-chemistry example of state functions and path functions. So state function, change in energy, final minus initial, we're going to kind of expand the subscripts here and make it match a reaction. The final state, well, I mean, that's just the product of the reaction. The initial state is the reactants. So energy of the products minus energy of the reactants will give you delta E for a reaction. So as an example, this first reaction that I have is solid carbon plus O2 gas making carbon dioxide. If on my energy scale, I have the carbon dioxide and the carbon solid and O2, the energies of those placed on here. Because obviously we haven't talked about how to calculate these. It's going to take us the whole module to get there. So let's just say that these are the energies of my reactants and products. The way this reaction is written is that my reactants are the carbon and oxygen. The carbon dioxide is my product. To go from reactants to products, I'm going down in energy. my delta E in this case ends up being negative. So I have a negative delta E overall for this reaction. What that means for how energy is flowing is that it's going from the system to the surroundings. The system is my reaction. If the system energy is less than 0, so it's giving off energy, the energy of the surroundings has to be greater than 0. The surroundings are absorbing that energy. If I flip my reaction, so carbon dioxide turning into carbon solid and O2 gas, the energies of carbon solid and O2 gas don't change. The energy of carbon dioxide doesn't change. But what does change is the direction my reaction goes. So I'm going from CO2 to solid carbon and O2. I'm going up in energy when I go from reactants to products. The delta E for this reaction is positive. It's greater than 0, which means that energy has to flow from the surroundings into the system. So for my reaction to absorb energy so it can go, it has to get that energy from somewhere. So it will absorb that energy from the surroundings, which means that the surroundings are giving off energy and the surroundings have an energy less than 0. So the summary is that, right, the delta E of the system is equal to the opposite of delta E of the surroundings. This is just law of conservation of energy. We didn't lose any of it. We just moved it to a different place. And if something is giving off energy, the other thing is absorbing that energy. And we will use sign conventions to tell us whether energy is flowing into or out of system or surroundings, what's being given off, what's being absorbed. The way that the energy is transferred, we will deal with 2 components. So the energy is transferred with heat and work. So in my system and surroundings, overall, my delta E, the one work component, I could have work flowing from the system into the surroundings, from the surroundings into the system. We use a lowercase w for work. Heat, again, flowing into the system, flowing into the surroundings. We use a lowercase q for heat. And overall, my delta E is Q plus W. Now, up until this point, I have labeled system, I have labeled surroundings in subscripts. You will see at this point, a lot of places leave the subscripts off. If it's a delta E with no subscript, it means the system. So the delta E of the system is heat plus work. Unit-wise, primarily we're going to be in joules or kilojoules, but there are a lot of other units for energy, some of which you're probably familiar with, and can potentially use, although when you see how we have defined some of these units, you may question everything you know about nutrition labels. So another unit of energy that you're probably familiar with is a calorie, but 1 calorie with a lowercase c is equal to 4.184 joules. 1 calorie with a capital C is the same as a kilocalorie. So instead of saying kilocalories, we put a capital C on the word calorie. So 1 kilocalorie or capital C calorie is 4,184 joules. Now, the food labels that you're looking at, when it tells you the number of calories, it is using capital C calories. So something doesn't have 100 calories, it actually has 100 kilocalories, because a calorie, 4.184 joules by itself, is a pretty small unit of energy. You might also see kilowatt hours used for energy. I mean, mostly when it comes to talking about electricity, but a kilowatt hour, since a watt is a joule per second, a kilowatt times hours gives you 3.6 times 10 to the sixth joules. Now, I mentioned the sign conventions that tells us how energy is moving. Let's just define all of them right now. For heat, which remember is Q, if you have a positive value for heat, the system is gaining thermal energy. If you have a negative value for heat, the system is losing thermal energy. For work, a positive value for work is work done on the system. A negative value for work is work done by the system. So another way to say this would be a positive value for work is work done by the surroundings, and a negative value for work is work done on the surroundings. The delta E overall, if it's positive, overall energy is flowing into the system, negative energy flowing out of the system. Have an example that we can look at to make sure our sign conventions are all set up correctly. So a system releases 622 kilojoules of heat and does 105 kilojoules of work on the surroundings. What is the delta E? So heat, it's 622 kilojoules, but it is released by the system. So Q for the system is negative 622 kilojoules. And the system is doing work on the surroundings. So that 105 kilojoules from the perspective of the system is negative. It's doing work on the surroundings. So the work is done by the system. My delta E is Q plus W, so negative 622 minus 105. My total delta E is negative 727 kilojoules.